Never could eat a whole orange. The outside's just too tough. Okay, so last time we were here, we were talking about inductors. And in doing so, we talked about Faraday's law briefly, which showed that the EMF generated by a changing magnetic flux, which can be written as a delta phi or a delta t, or more commonly as a, if you want to do calculus, d phi or dt. This was Faraday's law. It shows us that we can generate a voltage from a changing B field in some amount of time. Now, Lenz's law is very similar to this, and we saw this in the last video as well, but technically what we're going to see is that there is a negative that goes in front of this. And that negative has to do with a right-hand rule that we're going to talk about right now. This is a right-hand rule video. And this right-hand rule dictates the direction that our current is going to be flowing here. And it's really all due in part to a conservation of magnetic fields, or conservation of magnetic flux. So let's imagine for a second that I have some flux. Here's some flux, and it's traveling this way. And here is some, conductive ring I have. If this flux is 0 to begin with, when I put this flux through, now I have some positive flux entering into the ring here. I cannot just generate a magical positive flux out of nowhere, okay? This ring wants to conserve its flux, and it starts with 0, so we need to keep it 0. So if I gain flux this way, that means something has to happen with the ring in order to generate a flux going the other way, and this will keep things net 0. What it will do here is it will generate a current, and this current it generates will give us a magnetic field, which will create a flux going in the opposite direction. Okay, so we can do this few ways if you'd like to think about it. One way is to think about, if I have a flux coming this way, then I need to get a flux going the other way. That's the negative sign there. And to do that, if my thumb is following the current, my fingers need to go in on this side. So I can see that if my thumb follows this around this way, that will work. The other way to think about it is wrap your fingers in the direction you think the current will flow in this conductor, and the direction your thumb points, that's the direction that your opposing EMF will go. So another way to kind of think about this, and this is something that we see in the big cheese, this is a somewhat more common problem. Imagine that we have a uniform B field acting out of the page. Okay, so this B field's uniform. And on the left here, we have just some wire loop. Okay, if this wire loop begins to move into the B field with some velocity, what direction will a current be induced in this wire, in this green wire we have here? Well, if we look at the outside here, it starts at 0. There's no flux. Okay, the flux is 0. As we move into the B field, though, we're gaining some flux coming out of this system. So that means we need to oppose this change. We need to put flux back into the system. Okay? If I need to put flux back into the system, well, I'll take the flux, my thumb, I'll put it into the system, and when I wrap my fingers, I see that my fingers are actually going to go around in this clockwise direction. So the current here will actually be moving clockwise. Okay? If it gets all the way down here and we start pulling it outside, or pulling it out of the B field, well, we have some flux coming out, but we're losing it. It's all going away. Oh no. Well, we can't let that happen. As it starts to decrease, the flux starts to decrease, we need to keep it the same value. So we're going to pull more flux through in the same direction, so out of the page here, and when we wrap our fingers, we're actually going to find that our current will go, our current's going to go this way in a counterclockwise direction. Okay? And that's just, we need to prevent the change in flux. So whatever is happening, we need to prevent it. On the first one, we were gaining it, so we need to oppose that B field and lose some. On the second one, we were losing it, which means we needed to increase that B field coming through, so we had a counterclockwise scenario. Okay? There's a third case here what happens when you have a B field? I'll just redraw the B field real quick. 1, 2, 3, 4, 5, 6. It's uniform. What happens when you're entirely in the B field and then you're being pulled along? Well, when you're in the B field, you have so much flux going through you, and when you stay in the B field, that flux didn't change. Because there's no change in flux or a deflux, there's not going to be an EMF. So when you're completely inside there, you get nothing. There's no induced current that you have. Okay? So this is just one way we can think about the direction that these induced currents goes. Faraday's law is just the change in flux divided by amount of time. It becomes Lenz's law whenever you add that negative sign. And that negative sign is just the right-hand rule. It is just a convention. It's a convention given to us by the right-hand rule as to what we will see. So if you're just looking for a magnitude, you really don't care. But the right-hand rule really works that out for us and what's going on there. Okay? What's really cool here is that this EMF, if we do recall, this is a voltage, which means that if we're able to find a change in flux in amount of time to get this EMF, to get this voltage, we can also say V equals IR, and boom, we've just found our way back to Ohm's law. And we can go back to circuits through using magnets, which is a kind of a wild thing, and we'll see some of that later on when we start looking at some more complicated induction problems. But until then, we are finished here. Whoa, why is that in pink? That's got to be in yellow. Fin in 3D. Until next time, adios, and take it easy.